Welcome to Binding Blocks. I'm here with our 3D chart of the nuclear isotopes down at the hydrogen end, and I'm going to talk about fusion energy. Nuclear fusion is the process that powers the sun and all of the stars in the universe for that matter. The enormous temperatures and pressures that are at the center of the stars force the nuclei together. They overcome the electrostatic force and they stick together to form new, slightly larger nuclei. Fusion reactions release energy because there's a slight mass difference between the starting nuclei and the products, and this mass difference is converted to energy. Stars can start from hydrogen and, if the conditions are right, produce all elements all the way up to the most stable element, which is iron 56. The nuclear chart shows the amount of mass excess energy per kilogram of every isotope of every element in the periodic table. And the number of neutrons increases if we go across the chart this way, and the number of protons in the isotope increases if we go across the chart this way. Every layer of bricks in each tower represents 25 terajoules of energy per kilogram of the material. So that's 25 million joules of energy in 1 kilogram of whichever isotope you're looking at. And so that means that the tallest towers represent isotopes that have most energy, and then the shortest towers towards the middle of the chart have the least energy per kilogram, and therefore they are the most stable isotopes. We can use the nuclear charts to look at the amount of energy that's released in any fusion reaction. And the reaction I'm going to look at now is that between deuterium, which is here, and tritium, which is here on the charts. And these are both isotopes of hydrogen. So if hydrogen is a single proton, we've got red tennis balls for protons. Deuterium is adding a neutron. So blue tennis ball for neutrons. We've got a deuterium nucleus. If we add another neutron, we get a tritium nucleus. So if we take our deuterium nucleus and our tritium nucleus and we fuse them together, we end up with products which are a helium nucleus, which has got 2 protons and 2 neutrons, and a neutron by itself, which goes flying off with most of the energy that's released in the reaction. So the reason we've chosen to look at deuterium and tritium today is because that's the reaction that's been picked for fusion energy research here on Earth. We're trying to make what we call a star in a jar. So take fusion reactions and harness them on Earth to create energy, to create electricity. And the reactions that happen in stars between hydrogen atoms, they need much higher pressures than we can get here on Earth. So we have to pick a reaction that's more efficient at temperatures and pressures that we can achieve in the lab on Earth. So that's why we pick deuterium and tritium. So just how much energy is released in the deuterium-tritium reaction? And we can find out by looking at the chart. So deuterium is here. So if I take this tower, this is the amount of energy that 1 kilogram of deuterium has. So we're going to react that with tritium. And the tritium tower is here. So this is the energy of 1 kilogram of tritium. But because tritium's got that extra neutron, we have to react 1.5 kilograms of tritium with the deuterium so that the reaction's nicely balanced. So I've got an extra 0.5 kilogram here. And our products are helium. So helium's right down. It's a pretty small tower, so it's tricky to see. But this is our helium tower. And because helium has got 2 protons and 2 neutrons, we have to create 2 kilograms of helium to balance our reaction. So it's there. And we also create our neutron. This is the neutron tower. It's the tallest tower in the chart. But we only create 0.5 kilogram of neutrons because the neutron is only half as heavy as the deuterium nucleus. So those are our towers. So by sticking these towers together, we can visualize how much energy is released in the fusion reaction. So if we take our deuterium tower of 30 layers and we stick it together with our 1.5 kilograms of tritium, which is a total of 36 layers. So that's the energy of our reactants. And we take our two stacks of 7 bricks for helium and 18 for the neutron that's released. This is the tower for our products. So the tower for our reactants is 66 layers, and the tower for our products is 32 layers. So that's a difference of 34 layers, which represents the energy released when you do this reaction. So we're releasing 850 terajoules of energy per kilogram of deuterium burned. In the UK in 2012, one person used 1/8 of a terajoule of energy over the entire year. And we've released 850 terajoules of energy from burning just 1 kilogram of deuterium. So that's an enormous amount of energy. And another way of looking at this enormous amount of energy is if we take the deuterium that you'd find in half a bathtub full of seawater, and you react that deuterium with the tritium that you can get from the lithium in a laptop battery. So we've got half a tub of seawater, 1 laptop battery, and that would create enough electricity to power one person's life for 30 years.